So first of all, I'm glad to be in this very special AI seminar, though I will need to talk to some of you to figure out why it is special, because it's definitely not me. And while Tianpei suggests that this is going to be an awesome talk, I'll try to live up to that expectations. All right, so my name is Yeoh. Thank you, Matt, and the rest of you as well for coming to this talk and for hosting me. I'm here for 2 weeks as part of the visit. I'll be talking about explainable planning and decision making. And when I was designing this talk, Matt suggested that I try to make this more easily accessible to folks because the audience is mostly going to be students. So my goal in this talk, instead of wowing you with details of why my work is awesome and cool, I'm going to focus more on introducing and describing what is the problem that I'm trying to solve. And talk about some research challenges in that space, what our group has been working in that space, and wrap up with some open research questions that I hope can lead to some interesting discussions. And also, hopefully, this is going to be interactive. I hate to be the one talking for 1 hour, and feel free, if you have questions to ask, definitely interrupt me midway, all right? Okay, so if this works. So I'm not sure how you've had this feeling, but I did when I first got my Roomba many, many years ago, a couple of years after meeting Matt, so not. And when I got it out of the box and put it in my room to move around to get to work, I was curious why it's behaving the way it's behaving. It's moving around somewhat randomly, and I was thinking that if I am the vacuum cleaner, if I'm vacuuming a room, I'm probably going to vacuum it in a more systematic fashion, like a grid-like manner to vacuum it. Right? Why is it moving in these weird angles? And I wish I could ask Roomba then, and maybe if I could ask Roomba now as well, why is it doing these things? Right? Why is it not following walls? Or why is it moving around in circles? Why is it moving back and forth repeatedly sometimes and not some other times? And it'd be great if Roomba could basically respond and say, hey, I'm not following walls because A, maybe I have no idea what walls are, or I'm not following walls because you placed me in the middle of the room, so I do not know where the walls are, even if I knew what walls are, right? And why is it moving back and forth? This one I actually figured out from the Roomba manual, that it's moving back and forth when the floor that it is going over it detects that it's dirtier, so it's basically going back and forth to clean up a little bit more. Moving in circles, maybe, hey, if you could say that I'm moving in circles because my right wheel is stuck or something like that, right? These are the types of explanations I wish Roomba could give me. And so this kind of motivates the whole problem, which is, if you have some sort of a planning task, like a Roomba vacuuming a room, the robot having some sense of how the room is like and how the robot works is going to have some idea or some plan for how the robot's going to do that. You, on the other hand, you're going to have some model of the world as well, model of how the Roomba works, right? And you are going to have some plan of how you think Roomba should be working. And when these two things are consistent, right, everything is good, right? Because the Roomba is working exactly as how you thought it would do. And when these things are inconsistent, when there's some divergence, this is when explanation is needed, right? So this motivates why explanation is needed. And in this talk, for the most part of this talk, I'm going to assume that the robot's model over here is the correct one. Right? And if this is the correct one and things are inconsistent, that means that the human must be the one that's wrong. And here's where usually people are like, huh? Is this a good idea? Right? So to start off with, I guess, if you're thinking that the explanation is coming from the robot, naturally the robot is thinking that its model is correct, right? So explanation is with respect to its model. So even if the robot is actually having a wrong model, the explanation has to be with respect of its model. And just to start with, it's easier to just assume this is correct. But you can imagine that this correctness or wrongness of the models, it could, in the real world, probably, both of these are partially wrong somehow, okay? And so the high-level idea of how you want to get explanations is that you want to reconcile these differences between the two models, because the planning task is the same task for both models. And so if there's a difference, it must basically come from the model itself, right? So how do we figure out what the differences are in the models and reconcile them so that the two plans are going to be consistent? Make sense? So more formally, this is called the model reconciliation problem. This was introduced in the planning community, and you have two knowledge bases representing the models of the robot and the human. So KBA is the model of the agent or the robot. KBH is the model of the human. And you have some query Q, which is some question the human wants to ask the robot. And this Q here is true in the knowledge base of the robot, so it's entailed by KBA, but this query is not true in KBH. So you can think like, why are you moving in circles, right? Moving in circles is the query, right? And the robot knows why it's moving in circles. The human doesn't understand why the robot's moving in circles. And you want to figure out an explanation, which is this tuple here of epsilon plus and minus. And this epsilon plus here is the information that you would get from the robot that you want to give to the human. And the epsilon minus is things that you want to remove from the human to make this consistent, right? Because when you give explanations, when you give information from the robot to the human, it could be that now there are some inconsistencies in the human's model now. Maybe it previously thought that, for example, both wheels are working. But one explanations come epsilon plus is that my right wheel is stuck. So now in the human's mind, the right wheel is stuck and the right wheel is also working, right? So there's this inconsistency there, and we're going to figure out what you need to remove to basically get the updated model to still entail the query. Yes?
Do you have to remove information? Like whatever, I just have no idea.
Yeah.
So I just need information, but I'm not like altering a piece of my knowledge.
Yeah. So epsilon minus here could be empty. And in the same spirit of that question, it could be the epsilon plus could be empty too, because maybe you thought it should be going straight because you had some misunderstanding of how the robot works. So if I remove this misunderstanding, then it would be okay. So epsilon plus and minus could both be empty. Yes?
And does the human's knowledge base only change through these?
Yeah, so here, initially, this is the knowledge base of the human. After the explanation is given, the updated human knowledge base would basically be this one here, which is now...
But the explanations are the only thing that would change the knowledge base. The human wouldn't observe the agent and just change its knowledge base on its own.
Yeah, no. So in this context, the only way things are updated are through the explanations. Great. Any other questions? Yes?
So in the structure of knowledge base, is it explicitly like a list of facts? Like what if it is some sort of neural network or something like that?
Yeah. So in this, in the problem formulation itself, it doesn't matter. It could be a list of facts or it could be a neural network. The work I'm presenting over here assumes that it is a list of facts. Any other questions? All right. So so here you can see that the mapping between this problem and this figure I talked about earlier would be quite easy, right? KBA and KBH are basically the models of the human and the robot. Query here is something related to the robot plan or the robot's action. This could also be related to, why isn't the robot doing something that it is supposed to be doing, right? And then you want to find epsilon plus in the robot's model, epsilon minus in the human's model. You bring this over there, right? And then the updated human model would now entail an updated plan, and both of these are now consistent, okay? And so given this problem definition, or problem specification, a bunch of research questions, obvious research questions can come up. As computer scientists, you would think, all right, how do we compute these explanations effectively or efficiently, right? That's going to be an easy one that we want to do. Another one could be, how do we differentiate between two explanations? How do we know if one is better than the other? And there's actually a duality over here because some explanations might be easier to find and some explanations are harder. So you can think over here, given this problem definition, there's actually a trivial explanation that can be found in constant time, but it's a really, really bad explanation, right? And the trivial explanation is epsilon plus is the entire knowledge base of the robot. Epsilon minus is the entire knowledge base of the human, right? That would satisfy this problem definition, right? This is like basically Roomba saying, all right, forget everything you know about the world. This is everything I know about the world. Assume that is true. That is why I'm doing what I'm doing, right? But that's obviously a really, really bad explanation, right? Yes?
Your conjunction and the set difference, are they ordered or not?
Are there what?
Ordered.
Yeah, so you want to add the epsilon plus first, and then
trivial explanation doesn't work because they may be very similar, and then you do the union.
Oh, yes. Yeah, then I guess you should remove this one first and then add this one. Yes.
Good question. You said you were confidently said that will be very bad explanation. How is equality defined?
So I'm thinking it as bad as how I, as a human, would like that, whether I would like the explanation from my Roomba or not. It's bad, I think, because the information that's provided might be unrelated to my query. It might be unrelated to the plan. For example, how Roomba is charging, right? It's unrelated to why it's moving around in circles. So I'm getting more information than I need that I don't really need to know.
Okay, so let me ask a follow-up question. So are you going to define it? I mean, there's a bullet here which says how to measure the goodness, right? I think that's important, right? Because just saying something obviously bad, well, maybe it's obviously bad to one person, but maybe not so much to somebody who works on Roombas and is a Roomba engineer, right? That actually gives information to them.
Yeah, so there'll be a slide on this, but the spoiler here is that I do not know what the right answer to this is, but I'll propose several possible answers that I'm thinking of. Yeah, good question. Any other things? All right. So, and then, once you find explanations, you could be, all right, usually in CS papers, the problem is solved, right? You can publish it already, but in the real world, these explanations must actually be conveyed to the human as well. Finding it from Roomba's perspective itself, and Roomba thinks explanation is great, that's insufficient, right? Can the human actually understand that explanation? Maybe they might misunderstand the explanation. How do we convey things efficiently? And then the fourth bullet here, this is a common criticism of this problem formulation, which is that makes this ridiculous assumption that you must know KBH. Roomba must know your mental model before it can find an explanation. Right? That's obviously an unrealistic assumption. So how do we relax that? And then the last one, this is what happens if Roomba's model is also wrong. Yes?
Let me challenge that. Is that possible to have a universally good explanation regardless of the audience?
I personally doubt it. But
then the explainer, the Roomba, needs to know something about the audience.
Yeah.
Which you seem to be saying that knowing something about the audience is a bad thing, right?
Yeah. So here it is. It's saying that it knows everything about the audience. Like it knows everything about the human model, right? I think that is a bad thing because it is an unrealistic high bar to reach. But maybe knowing something that is easier to obtain from the human, that would be better, right? So if you know, let's say, an approximation of the model of the human, whether this is a Roomba engineer or it's a layperson in the house, right? That might be better. Yes.
But then there's another question. It's not just the audience; it's also the purpose of the explanation, right? Depending what you want to do with the explanation. If only I care whether I should lift it up and get it out of its wheel stack, that's one explanation will suffice for that. But if the purpose is to improve Roomba, and I happen to be a Roomba engineer, I'm probably looking for some very different explanation, right?
Yep, absolutely.
So is the purpose somewhere here in this formulation?
No. So how you use the explanation, that is not part of this problem definition, right? So for example, are you using it to debug it, to understand it? Are you using it to fix Roomba? That's, I guess, the explainable planning community, and at least for this problem formulation, that is considered out of scope. But that is actually...
That seems to be critical, right?
Yeah. I absolutely agree. Yes?
Just a quick addition to what Vadim was saying. So here you're talking about a query queue, and you said that the goal is to make it so that KVH is queue. So I think another trivial answer to find like a minimal knowledge base that just contains Q, but tells you nothing else about the world. And that kind of plays into what Vadim was saying, because that knowledge base is solving like the immediately posed problem, but it's not going to answer any other questions at all.
Yep. Things like generalizations and so on, right? So you could give the explanation that the Roomba is moving in a circle because it is stuck in this floor area, right? It's not because the wheels are broken or something. Yep. Awesome questions. Great. So let me go to first part first, because this will also more concretely quantify what exactly is an explanation and so on, and how we've been using it, how we've been solving it. So we're going to use this very simple toy example. In the grid world, Roomba is up here top left, right? And the robot thinks that this is the map of the house, and this is block cells, and it needs to clean these two areas, C1 and C3. And the human thinks that, right, B1 here is not blocked, but the robot thinks it is blocked. So you can imagine that in this problem, once the robot finds the plan, the robot's going to do this, and here the human's going to wonder, why are you doing this? It will make more sense to just go down and right. So that's when the two plans need to be reconciled. So before we solve the explainability problem, I'll talk about how we solve the planning problem first, mapping it into Boolean satisfiability or set problems. So you can have Boolean variables indicating facts about the world. So for example, the starting robot location, like A1 at time step 0, the robot is basically here, right? And at time step 0, it is not at any other locations. You can have variables indicating whether a cell is blocked or not. So if like A1 is not blocked, B1 is not blocked, etc. You can have some goal states that the Roomba needs to be at a particular location at some time step t and t prime in the future. And so these are just planning specifications, right, for this map. And then there's also action dynamics of the robot. Like basically, if the robot goes down at time step t, and it is at A1 at time step t, so it's here, and B1 is not blocked, then the next time step is going to be at B1, right? And if B1 is blocked, then the next time step is going to remain where it is. So you can have a bunch of rules specifying what happens when the robot takes different actions. You can also have constraints, for example, that encoding that the robot can only be at one location at any time step. So if it is at A1, that means that it is not at any other locations. So you can have all these different representations using Boolean variables. And all of this is essentially what's in KBH. Right? And hopefully that answers the question about what exactly is in there. In this work, we're basically using Boolean satisfiability formulas to represent what's in the KBH. In KBA, you can imagine that it's exactly the same thing, except that B1 here is blocked instead of not blocked. Right? That's the only difference. Okay? And once you model this as set, you solve the planning problem. It's actually fairly easy to solve it using set solvers, and tons of efficient ones exist these days. And you're basically going to get these two plans for the two models, right? Human's going to basically go down and right. Robot's going to go this way. And then the question of the human is like, why are you doing this instead of this, right? And here, this is just one example query. You could also have other queries like, why going this would not achieve the goal, or why is this the shortest path, or those kinds of queries could also exist. Right? And so now that then we can define the model reconciliation problem. And here the answer is quite easy. The epsilon plus and minus is essentially, epsilon plus is block B1, epsilon minus is not blocked B1, right? Because if you replace the KBH with this information here, it would also then entail this plan, right? And here it is a simple solution because the only difference is B1. But you can imagine that if this map was larger, there are row D, E, F, or whatever, right? And if there are differences between the robot's model and the human models in these rows, right, those differences actually do not need to be communicated, right? So if our goal is to find the minimal amount of information to communicate, right, then this would be it. Make sense? Okay. So, and then how do you find this epsilon plus and minus? Then you can go into algorithmic details. you can use, for example, heuristic search to go through the space of all possible combinations and search through that space and check one by one and see which one work. We have also tried it using logic programming techniques, specifically answer set programming. So for those who are not familiar, it's basically like integer programs or mixed linear programs, except that it is using logic. We've also solved using hitting sets and search. And hitting sets are ideas that are popular in diagnostics. And I'll briefly talk about this one next. But any questions before I go there? So hopefully this now concretizes what exactly the problem is to be solved, right? Okay, hitting sets. In diagnosis, there's these two notions of MUS and MCS that's popular. MUS is minimal unsatisfiable set. It's basically a set where, given an inconsistent knowledge base, what is the smallest subset that is still inconsistent? Okay, and MCS is that given inconsistent knowledge base, what is the smallest subset that I need to remove from the set such that the complement, the remainder of that set, is now consistent? So how do you fix it, right? So, and we are using this to for explainability to find epsilon plus and minus, and because there's this very nice similarity there. And epsilon plus, we use MUS to get epsilon plus by basically saying, all right, we have KBH that is consistent, KBA that's consistent, the robot's knowledge base that's consistent. I have a query that is entailed by the knowledge base. And if I add the negation of the query into the knowledge base, now it's not going to be consistent anymore. It's going to be inconsistent, right? Because if you add the query itself, it'd be great, but if I add the negation, then it's inconsistent. And then I want to find what is the smallest subset in this updated KB that is still inconsistent. And this smallest subset is going to be the support for Q. So you can think about, if I have a knowledge base, right? What is the cause for why not Q is inconsistent? And this subset is basically going to provide that information. So you can use MUS to get the support for queries, and that's essentially epsilon plus. And then once you put epsilon plus inside KBH, now it's going to be inconsistent now, right? Or it could be inconsistent. And if it's inconsistent, I want to fix this. And how do I fix this? I want to find some minimal subset to remove to fix it. And that's basically MCS, right? So I use MCS then to get epsilon minus. Right? And there are tools out there that can find these sets quite effectively because they are commonly used in diagnosis. And we also exploit some duality between MCSs and MUSs. There's some relationships here that allows you to compute things more efficiently and also get approximations and so on. Right? So we did this for AAAI paper. And yeah, so that's to find explanations. Okay. Now we get to some of the other bullets. How do you find the goodness of explanation? Here, like I told Vadim earlier, I do not know what the right answer to this is. And I suspect there is no right answer, right? Yes?
Wait, sorry. So in previous slide, you said this is a way to find an explanation. Is that like the only type of explanation that is there?
No. So over there, we are optimizing for the minimal size, right? Because like the MUS and MCS, they're finding the minimal subsets, right? So that can be used if your goal is to find the smallest epsilon plus and smallest epsilon minus possible. But if your goal is to find something else, then MCS and MUS might not be the way to go, right?
So I wonder if that relates to like measuring the goodness. Like maybe you need a little bit more. It's not like necessary, but it is beneficial.
Absolutely, right? So we started off by trying to minimize the length of explanation because I think that's a natural objective to want to think to do, especially as computer scientists. But after we did that and think about it further, that is not the only way, and that might not be a good way. You can imagine that if I have a short explanation that is very hard for you to understand, and a real longer explanation that's easy for you to understand, maybe the short explanation are using terms that you do not know, and the long ones are using terms that you know, right? Maybe the long one's better, right? Or it could be some explanations are easier to convey than others. You can imagine that if some explanations I need to use the blackboard and draw crazy graphs and so on to explain, and another one I can just show you as one simple graph that tells you that, or I can just tell you in a sentence, right? That might be better. So that could also be taken into account. And the last one here, this might be a bit more ambiguous on whether this is the right thing to do, but maybe you want to find explanations that that is more convincing in the sense that the receiver of the explanation is more likely to believe you. You looked at the question.
Yeah. So right now you've shown that the knowledge base of the human is almost like a ground truth knowledge base, but in like actual application, the way humans would understand the world is very different. So how are you going to go about aligning the knowledge base of the human with potentially matching facts?
Yeah. Great question. At least for in the model reconciliation definition, that because we assume the knowledge base of the human is available, that's not an issue because of that assumption. But you can imagine that in the real world, you would then need to have the same language, right? Maybe if a robot was speaking French and you're speaking English, right? The vowels in French and English might be different things, and how do you have that equivalence? So that's another question as well. So I guess in this work, we would require that they both at least have the same vocabulary, so that we don't have to worry about this translation. Yes.
So a little bit more on this. So it seems like all of your bullets here hinge on the term understanding, because you want the human to understand. I would argue that there is no sort of universal understanding, that it's purpose specific. I can say I understand airplanes enough to get on them and fly, right? Not as a pilot though, right? But an understanding of flight for a pilot is something different than understanding for flight for a passenger, right? Even the same person with all the same background, they may require different explanations for different purposes at different times. So if we just reduce this to the concept understanding, we're just passing the buck, because the word understanding is so big and so task and person specific, perhaps, that's not really helping.
Yeah, absolutely. Right. So, and that's why I don't have a good sense of what's the right answer here, because it depends on a lot of things of how explanations are going to be used. Like what questions of different levels of understanding of the human, whether this is a plane pilot or plane mechanic or passenger, you want to have different explanations. So explanations might need to be a different granularity. You might need to use different words or different vocabulary depending on who you want to explain this stuff to, right? We have some work in the vocabulary space, but it's still preliminary ongoing work, right? Mm-hmm.
Yeah, I was gonna add a comment with that. Yeah, I feel like whenever there's a human in the loop, so in this case, we want an explanation for the human, it's always personalizing to at least some subset of people. It's very hard to create, I think, something that, okay, this is universally gonna be good and everyone's gonna agree that it's good. Yeah, okay, yeah.
Yep.
Sorry.
Yeah.
I wonder if any of the two approaches may be useful. One is like having like a utility function on the different objectives. So in different contexts, like different objects may need to be weighted differently. Another one is, of course, having a human in the loop, but the human can like give feedback of like how understandable it was and so on, and then that can be used to optimize in the next step.
Yeah, absolutely. You can think of that as a learning problem, trying to figure out what the preferences for what kind of explanations the human wants. And this will also go into the context of trying to learn and approximate the human mental model as well, right?
Yeah, so I was just wondering about how you choose the level of abstraction for explanation, because I do work with Roombas, and then if the Roomba is going towards its target, so let's say it's using IR sensors, right? Even if it tells me something about, oh, the IR sensor beeped so many times and that's why I'm going there, I'm not going to understand it. For me, I have this model visually, but there is, I guess one of the assumptions here is that there is some intersection of this knowledge piece where some level of abstraction where the Roomba would say something sensible, which I can parse too. So how do you go about choosing something like that?
Yeah, so this would go to the abstraction level bit, like, what another question, I guess, that I didn't talk about here would be, what is the right abstraction of explanations needed for the human? And if you know KBH, then you might be able to find that abstraction level more easily, because if KBH doesn't contain how IR sensors work, then you might not want to use IR sensors, right? And the work that we did that I can share later after this talk is trying to approximate explanations using as much as possible the language that is understood by KBH, right? Using literals that already exist in KBH, as much as possible, and only introduce new literals as needed, if absolutely necessary.
Okay.
Oh, sorry. Yeah.
So I noticed that the list of requirements that you have doesn't include that ABH should be true after it is some plus and minus is added. Like, is it okay for the agent to mislead the human so that it doesn't think
Absolutely. In the sense that it is not defined, whether that's as the problem is defined, it allows for that, right? Whether that's a okay thing to do, an ethical thing to do, that's a good question. And in fact, when this problem was first defined, there were papers saying, is it okay for robots to give white lies, right? If I lie by omission, is that okay? Because essentially, if you have a misconception and I don't correct you, and I don't correct you because your misconception allows makes you think the plan is correct, right? That would satisfy the requirement, right? And at least in the planning community, I don't think that's the right community to solve that question. Vadim, I guess you had a question?
Yeah, so I was wondering if you're going to talk about using natural language systems as prompts to the human. So we're doing quite a bit of recent work trying to use ChatGPT as a measure of where the explanation is understandable, like whether ChatGPT can do something without like write a code about it or whatever. I think Wendy and others have done this work, and my group also did a bit of that as well.
Cool. Yeah, we didn't use LLMs yet for that purpose, but I could imagine that that could also be LLMs could be used to quantify how good an explanation is. But then that also raises the question: is the LLM's quantification of how good an explanation is that a good way to quantify how good an explanation is as well?
So you assume the human is incorrect and the robot is correct. But how do you distinguish humans and the robots? Because you can just say this is KB8, KB1, KB2.
Yeah. So here the robot is basically the agent that is providing the explanation, right? If you flip it and you have basically the human providing an explanation, yeah.
Maybe the robot model is incorrect.
Yeah. Mm-hmm. So correctness and wrongness, I guess, is from the perspective of who's providing an explanation. Okay. So short answer is lots of different ways. I do not know what is the right way, and most likely we'll need to collaborate with ethicists and so on to figure that out too, figure out what's a good measure to optimize. And then once we find an explanation, that's how do you convey that? So when I started this work, I was thinking visualizations is probably a very effective way because pictures paint 1,000 words. And so I was collaborating with visualization and HCI people to come up with explanations. And we found out that if explanations are about information or state information that maps to some real-world concept that can be easily visualized, then visualization is great. Right? So for example, in the Roomba example earlier with B1 not being blocked, instead of giving you logical notations or giving you English sentences, right, I could just show you a map and then show you that this particular cell disappears or appears. You would understand that perfectly. And there's also some work in the planning community about preconditions and effects of actions. Like if I want to execute this action, these things need to be true. And if after executing action, these things are going to be true. And you could have explanations that I need these 5 things to be true, but only 3 of them are true, and these 2 are not true, and that's why. Right? So you can have a sequence of actions that needs to be taken according to this kind of precondition effect requirements. But more recently, I'm interested in this dialogue-like explanation. Not surprisingly, ChatGPT and so on also influences and enforces that desire, because I think when we interact with people, at least, explanations that are provided aren't just a single shot and say, this is explanation, I'm done, right? It's usually a dialogue, and I'm providing you some information, getting some feedback, and providing more information that answers your questions, right? And so I wanted to go by that direction and use our argumentation as a way to enable that. So in this, preliminary work, we had a problem of the human trying to understand why a robot thinks C is true. So here, the goal is, again, for the human to understand from the perspective of the robot why it thinks C is true, even if the human disagrees that C is true, right? So this could be an example of, let's say, Roomba moving in circles. It could be why does Roomba thinks it's moving in circles, or if a diagnosis, if Roomba is doing something wrong, and I know what it is doing is wrong, I still understand why it is doing that so that I can fix it. Right? So here we have these two arbitrary KBH and KBA and some logical rules here, and this example also illustrates how this method, I guess, could be applied more generally than just planning. We have tried it in some scheduling applications as well. But essentially, you can think any application that could be represented in logical form like this, it could be used. Right? And so if you want to understand why C is true, the human might basically say, all right, that's a query of why C is true. The robot is then going to find a support for the query, and the support is basically going to say that, all right, C is true because A and B are both true, and since A and B are both true, A and B implies C, so therefore C is also true, right? And the human is now going to see, all right, it's going to refute C. It's like, I don't think C is true because in my understanding of your model, E is true, and E implies not C. And then the robot might basically say, refute that again and say, all right, you think that, but E is actually not true here, right? Your premise is not true because H is true and H implies not E. And the human has nothing to refute here because the human doesn't know H. And so just taking Roomba's word for it that H is true and H implies not E, will then accept the argument. And after accepting it, you'll then update its knowledge base, basically saying E is now no longer there, right? But this rule can still be there, right? Because you've just removed E, and then H, everything else here is added, and KBH, this updated KBH would now entail C, right? So this approach over here, first of all, relaxes the assumption that Roomba knows KBH, because everything that Roomba is providing over here is only based on KBA, right? And it could also use information of what the human says. So maybe like here, it could use information over here in its attack later on as well. But this would relax the assumption that KBH is known. And I guess further research questions along these lines would be, all right, how do we learn and approximate the human's mental model? Because since we're not using the mental model of the human in these explanations, if we could estimate that, that would be better, right? And this is also assuming that we know how humans would update information that it receives. And at least in a setting where the human is trying to understand why the robot thinks C is true, it makes sense that the human is taking the robot's word for it. It trusts the robot completely because it's trying to understand the robot. But in a setting where maybe the human and the robot wants to understand whether C is true, not why the robot thinks C is true, then how the human update their model is going to be different, right? It's going to be dependent on maybe how much the human trusts the robot or how much the human trusts what the robot said. Yes?
So when you say human wants to understand why the robot thinks C is true, the word understand here, I want to, what specifically does that mean?
Formally, it would be you want to find a KBH that entails C. Yes.
So on your previous slide, you were saying that if the human does not have information, I think like the two H's, and so the human says, okay, robot, I'll just take your word for it. Is also the converse true? If the human has information that the robot doesn't, will the robot also assume that it's not lying? The human is not lying?
In this case, yes. It assumes that the human is not lying. Mm-hmm. Yeah, so that's where the human might basically, for example, maybe say something about H not being true because whatever K is true, right? And the K doesn't exist here, then it's going to be basically, all right, I thought C is true because I didn't know K, right? But if K is not true, then indeed C is not true.
Yeah, I also had just another comment. So you were talking about learning like the mental models for the human. I guess there's also another body of literature in like the AI education space where they're also trying to learn human models, so that might be interesting.
Yeah, absolutely. And then this explanation stuff is also relevant there because, like, teacher, student, like the way you teach is you provide explanations for why you think C is true, and hopefully the student agrees and understands why C is true.
I just yell louder.
That's part of the conveying explanation bit, right? And yeah. All right, and then you'll notice that everything that I talk about over here in these logical notations, they're all in propositional form or Boolean satisfiability and so on, which is inherently, it doesn't capture stochasticity or uncertainty, right? Everything is deterministic. It's like if A and B are true, A and B implies C means C is definitely true, right? But in the real world, there's stochasticity, right? If robots moving around, there's uncertainty over there. There's uncertainty of what the robots estimate of the human's KB is, or there might be uncertainty on these rules. Like, for example, if this is true and this is true, maybe C happens at 80% chance. Right? Yes, Vadim.
It seems like if you were to allow predicates on these facts, and you could package them to incompleteness and therefore have some awkward support of uncertainty and probability.
Yeah, so actually all these, in practice, they are predicates, right? But even, I guess, with the predicates itself, it would still be deterministic in the classical planning sense. But but you could extend this, I guess, using probabilistic logic or Markov logic to have these kinds of probabilities. So you can think like, let's say in a case where I don't know, smoking causes cancer, right? So F is smoking, and if you smoke, you have cancer, right? That's not 100% chance, right? There's some probability attached to it. So there's work done on trying to extend or finding different, richer classes of logical representations that account for these uncertainties. And that's something we would like to do in the future as well. But the explanations itself would become trickier. Now you can potentially have conflicting sentences here, and it's okay to be conflicting because they are probabilistic, right? And then like Vadim was suggesting, LLMs. There are obvious ways, I think, or clear ways how LLMs could be used, like in evaluating the goodness, but it also could be used in the interactions, because right now between the robot and the human, what we have is logic interactions, right? Roomba is saying support C is A, B implies C, right? With an actual person, that's not going to fly, so you need to translate this into natural language, right? The human's not going to say this, the human's going to say natural language. You need to translate that into logic. So that's another way of, I guess, trivially using LLMs. But there could be challenges there, is that, in this translation, if there's inaccuracies, like, that could complicate things as well. Right? And there's at least, I think, some ongoing work on translation between logic and LLM, logic and natural language using LLMs. So that's another place to use, right? And to wrap up, I guess my goal over here, the short and medium term goal at least, is that I want to have a system that can interact with you just like ChatGPT would, right? And I want to have Roomba to be able to talk to you just like ChatGPT would. And I want it to not talk just like ChatGPT, but also be able to give reasons for its actions, explanations for its actions in a way that is grounded in how it understands the world. And that part is key to me. And in the longer setting, I guess this to me is a piece of a puzzle of my ultimate wish list, which is that we want humans and AI agents to work collaboratively together. Right? If you want them to work together, well, the humans need to understand why the AI is doing things, right? So explanation is needed. And there's some other work that I'm still doing, like goal recognition and all that, that's also within the space. So this is broadly, I guess, what my group is interested in doing. But today I'll just talk about the explanation bits. Right? And so for those of you who are PhD students, and if you do not know PhD comics, it's been around for quite a while. And if you do not know it, I highly recommend you go check it out. It's old, but it's still relevant. Some things in academia doesn't change. And so acknowledgements, I guess, a lot of the work, I guess, that over here that I talk about is being led by Yeoh, one of my PhD students who is hoping to graduate this year. and Ashwin's also helping out quite a bit, and Melanie was collaborating on the visualization parts of the project. Also like to thank, I guess, faculty collaborators and industry collaborators. Alvita is the Viz expert. Son, this guy got me interested into logic and pulled me into that space. Alessandro, he's an expert in heating sets. So we collaborated quite a bit on that AAAI paper. And Francesca is an argumentation expert who is helping us with the argumentation dialogue for explainability. Right, that's it. Thank you. Tons of questions during the talk already, but happy to answer more if you have any. Yeah.
Wait, going back to the argumentation, could you use that setup to try to figure out if the human is making some kind of logical fallacy or doesn't have infinite look ahead and is just being myopic when they're planning?
So the argumentation work can detect the human fallacy if what the human says is conflicting.
Okay.
Right? You can say, maybe here you say E is true and E implied not C, and later on you say E is not true, right? It could detect that. But how human uses his knowledge base to do the planning, it doesn't do that. Any other thoughts? Yeah.
Would you ever imagine explanations going like in parallel? So like the human is giving explanations and also the robot is also giving explanations, like one after the other?
Yeah, so that would be more in line with the human AI collaboration space, where you can try to imagine that the human wants to understand whether C is true or not, right? And the robot also wants to understand whether C is true or not, and maybe both of them do not know whether C is true or not, right? And then that's where you might want to find pieces of information that is needed to together combine to imply if C is true. But that's a much harder problem. Yeah.
Do you think like NLP or like LLMs are the best form of this, of all the explanations, or like should we be doing other types of visualizations or things like that? Is there any work on that? Like, yeah,
there's some work in the visualization ACI area that tries to evaluate whether visual explanations are better or text-based explanations are better or both of them combined are better. I think the conclusion is that it's very dependent on the explanation itself, right? If you're explaining if you're trying to explain calculus, then I don't think visualizations might be helpful, right? But if you're explaining things that can be visualized, like let's say routes of Roomba or like class schedules, right? Then visualizations are awesome. And I was in Japan earlier this semester, and they, I think, are the experts in visualization explanations, because I go there and I don't read Japanese, I don't speak Japanese, but I can understand their signs, or I think I understand their signs, right? Because they have these visuals that concretely gets to the point. Yeah.
This is a very naive question because I'm not really familiar with technology-based AI, but how realistic is it to be able to describe a human's knowledge base by a consistent set of logical actions?
Absolutely unrealistic.
And so how does this sort of system deal with like people holding inconsistent views that might be consistent with maybe more nuance, but
Yeah. So the way I guess folks answer that question would be to include uncertainty and probabilities in there, right? Because it's like, hey, one part of you thinking smoking causes cancer, another part of you thinking smoking is cool, right? And both of them can exist in your brain probabilistically. And when you add probabilities in that, then definitions of consistency becomes a lot looser.
And maybe sort of a follow-up to that. So it seems like so here we're talking about we have a set of facts and we have a set of things that we can deduce from those facts. But we're not really talking about the argument used, right? So for example, if fact C follows from A, but also from B, right? Like we just know C is true if A and B is true, but we don't know which of A or B we actually used, right? So it's like in maths, it's like you know there is a proof of a statement, but you don't know what the actual proof was. So is one of the aims of this kind of work for the agent to explain to the human, not just that something is true, but like why it thinks something.
Absolutely, right? So over here is like, I think C is true, and why C is true is because this thing. So you can think like this is the proof for why C is true, right? And then the conditions for that proof, the premise of the proof holds.
Yeah, but for example, let's say that A and B would both suffice to prove
Mm,
C,
mhm.
right? And then robot thinks C because of A, but it might tell the human that it thinks C because of B, and both of those are true in some sense, right?
Yeah.
So it's not
Yeah, so that would be in line. If there are two possible explanations, which explanation do you want to give, right? And then we'll also go into the space of, if you think A is true already, then I want to give you explanation that A implies B, or A implies C, right? And if you think B is not true, then I probably don't want to tell you that B implies C. And that also gets to the omission case, right?
Because some of those A or B might have status unknown, either the agent or the human. And then should you tell the human that no, this is true, even though you don't know it, or should I give you the explanation and you're likely to accept it on the what?
Yeah. So yeah, that goes into the goodness part, right? Mm-hmm. Anything else?
What were some of the ideas behind the goodness of explaining?
Yeah, so the ones that we have tried are the length of the explanation.
Is there anything that uses like a history of the past queries?
Not yet. So that's a good question, because right now the problem specification is such that there's a single query, and once you give the explanation, the problem is solved, right? But in the real world, you can think that there are interactions, there's a history, right? You might have queries that depend on previous queries and all that. That is open work, an open area. And that also goes into trying to learn what kind of explanations you like, because as I learned that you were very against B not being true, now I'm going to say, all right, I'm not going to tell you that B is not true anymore.
All right. Thank you again, Will.
Thank you all for listening.